Right, so in the previous class, we were talking about fixed length compression of IID sources. In particular, we focused on the case where Xn was an IID Bernoulli P sequence. The goal is to compress Xn into a fixed length sequence Ck, such that we can also construct a decoder or a decompressor which can recover back Xn from Ck with high probability. What does that mean? So K is fixed and hopefully much smaller than N, and from Ck you can recover an Xn hat, and you want to ensure that the probability of error, which is defined as the probability that Xn hat is not equal to Xn, is vanishingly small. Right? So as n tends to infinity, the probability of error tends to 0. And at the same time, you want to make sure that the rate, which is K over N, is asymptotically as small as possible. And the claim was that it is possible to construct a compressor such that the probability of error tends to 0 as n tends to infinity. At the same time, the rate tends to the binary entropy of P, so H2 of P for a Bernoulli P sequence. All right, and the basic idea was that you keep only those sequences which you think are important, essentially those sequences which have high probability. Sequences which have low probability can just be discarded because you don't care whether you're able to reconstruct those sequences correctly or not. Okay, and we'll build upon that idea, and I'll give a compressor, and I'll give the intuition behind why this is a good compressor, and why it achieves vanishingly small probability of error, and at the same time also achieves a rate close to the entropy. All right, and to sort of build up towards that particular construction, we saw a number of examples, simple examples, starting from the extreme case where the probability of a 0 was always equal to 1, or the probability of a 1 is always equal to 1. In that case, we saw that we don't have to transmit any bits at all, so K can be kept 0. But then if it is very close to 0, so for example, if we knew that the probability that the number of ones in Xn is exactly equal to 1, or if the number of ones in Xn is greater than 1, is vanishingly small, then we can actually achieve a very small K of just log n. And log n over n tends to 0 as n tends to infinity, so asymptotically the rate is also equal to 0. So now we are going to build a compressor for general Bernoulli P sequences which achieves a rate close to the entropy. But before that, are there any questions? Any questions? Okay, so the way our compressor works is as follows. You list all possible sequences for which the number of ones in the sequence is between np into 1 minus epsilon and np into 1 plus epsilon. Right? Because you know that, well, if you take a large enough sequence, then the number of ones that will appear in that sequence with overwhelming probability, the number of ones that will appear in the sequence is going to be very close to n times p. So we leverage that fact and look at this particular set. So the set of all sequences for which the number of ones in the sequence is between np into 1 minus epsilon and np into 1 plus epsilon. Okay, so we have this particular set, and what I'm going to do is I will only so the goal is to make sure that the sequences in this set are reconstructed properly. The other sequences we don't care. Sequences outside this set could always be in error, no problem. So So you basically list all possible sequences in this particular set. These are the sequences in the set S, and these are all the sequences which are not in S. Doesn't matter in which order you sort of write them down. Any order is fine. So this is S complement, whereas this is S. So for each set in S, you're going to assign a fixed length sequence in any arbitrary fashion, doesn't matter. So you order them out, and therefore you start with the all zero sequence and go all the way up to the all one sequence, right? So how many bits do you need? As we discussed in the last time, in the last class, the total number of bits that you need is log, so k is equal to C log of the size of S. Okay, so these many bits suffice. Now all of the other sequences in S complement, we'll assume that they're all mapped to the all one sequence. Okay, and what does the decode? So this is what the encoder does. The encoder just maps this to the corresponding sequence in the table. Now this table is sort of part of the code design. So the decoder knows this particular table. So what does the decoder do? If it sees any one of these sequences in this particular table, then it reconstructs that particular sequence in S. So for example, if the decoder is given as input the all zero sequence, then it outputs xn of 1. If it gets to see the all one sequence, then it outputs the last sequence in this particular set. So xn of size of S. Right, so this guarantees that any sequence in the set S is reconstructed exactly without error, whereas every sequence in S complement cannot be reconstructed. Okay, so every sequence in S is reconstructed exactly without any error, whereas every sequence which is not in S is not reconstructed at all, and therefore will always be in error. So therefore the probability of error is equal to the probability that you observe a sequence which is not in S, right? Or in other words, this simply means that the probability that, so remember that S is the set of all sequences for which the number of ones in S is between np into 1 minus epsilon and np into 1 plus epsilon. So therefore, this is the set of all sequences for which the fraction of ones is greater than epsilon. Right? The fraction of ones in the sequence is strictly greater than epsilon. And just by whatever bound you want, the weak law of large numbers, or even if you use Chernoff bound or Chebyshev inequality, it's easy to see that this probability tends to 0 as n tends to infinity. Right? So the probability of error is definitely vanishing in it, and that is what we want. We're happy with that. So such a set, any such set for which the probability that xn is not in S is vanishing in N, such a set is sometimes called a high probability set. Right? This is called a high probability set. So any set for which the probability that a random sequence drawn from whatever distribution is not in S, if this probability tends to 0 as n tends to infinity, then we say that this set is a high probability set, right? And this particular set, that is a set of all sequences for which the number of ones or the fraction of ones is less than or equal to p plus epsilon, is close to p plus epsilon, p minus epsilon. This is a high probability set. Okay, that's good. So now what is left? What is left is to find out what k is, right? Or in other words, we want to know what is k over n.
Excuse me, sir.
Yes.
Sir, sorry to interrupt.
Mhm.
Even today, you're not able to record, sir. In
So I'm recording my screen.
Okay, fine, sir.
So don't worry about that. I'm recording the screen, but yeah, I'm not able to record it via Google Meet.
Okay, sir. Thank you.
All right. So now what remains is to find out what k over n is, right? Or asymptotically, roughly what k over n is. Okay, that's fine. So, or in other words, equivalently, what we want to know is what is the size of S, right? Or because our ultimate goal is to find the seal of log size of S to base 2. Okay. So this is going to be an exponential sized set, and our goal is to eventually our goal will be to find out what is the exponent. Okay, so what is S? It is a set of all sequences for which the number of ones is between np into 1 minus epsilon and np into 1 plus epsilon. So firstly, what is the number of sequences of length n and having let us say m number of ones? What is this quantity equal to?
N choose M.
Exactly. So it is n choose m. Okay, great. So therefore, the number of sequences of having at least np into 1 minus epsilon and at most np into 1 plus epsilon. Well, obviously this is the size of S, right? So what is this equal to? What is this going to be equal to? So you already know this. You want to find the total number of sequences having at least np into 1 minus epsilon and at most np into 1 plus epsilon. I don't expect you to give a closed form expression, but whatever. So it is the summation, right? So m going from np into 1 minus epsilon to np into 1 plus epsilon of n choose m, right? Okay, so this is just a summation of binomial coefficients, right? Let us assume that p is between a 0 and a half, right? So p is between 0 and half, and let us further assume that p plus epsilon. So we choose a very small epsilon such that p plus epsilon is also between 0 and half. P plus epsilon and also p minus epsilon is also greater than 0. Okay, there's absolutely no loss of generality in assuming this, that p is between 0 and half, and basically everything works in a very similar fashion. Okay, so now if you look at all of these binomial coefficients, there are many of them over here. Which of these will be the largest binomial coefficient? For what value of m between np into 1 minus epsilon and np into 1 plus epsilon will this be the largest? Anyone?
M is near NP.
M is near
NP.
Okay, so if you take any general n choose m, okay, for you fix an n and then vary m from 1 to or 0 all the way up to n, where will this reach the maximum?
So the middle value in the range?
Exactly. So n choose m is increasing in m up to n by 2 or close to n by 2, depending on whether n is odd or even, and then again decreases as you increase m, right? So if you plot n choose m versus m, so this will sort of increase and then reach a peak and decrease, and the peak is exactly at n over 2. So you go from 0 to n, right? So the closer it is to n by 2, the larger the binomial coefficient is. So therefore the size of s can be upper bounded. So remember, it's a sum of terms, right? So it is less than or equal to, again you have summation m going from np into 1 minus epsilon to np into 1 plus epsilon of n choose m. The largest term will be n choose np into 1 plus epsilon. Right? Is that okay?
Sir, can you explain the last step? So how did you get this thing, sir?
Okay. So the point is that n choose m is an increasing function of m as you vary m from 0 to n by 2. Okay, and look at the range over which you are varying m in this particular summation. In this particular summation, so m goes from np into 1 minus epsilon to np into 1 plus epsilon, right? So m is always between np into 1 minus epsilon and np into 1 plus epsilon, and the assumption is that p plus epsilon is less than half. Okay, so among all of these terms, this is a summation of multiple terms. Each term is less than or equal to the largest term. And which will be the largest term? The largest term will be the one corresponding to m equal to np into 1 plus epsilon. Correct? Is this okay?
Yes, sir.
All right. So therefore, each of these terms, each n choose m in this series, in this summation, is less than or equal to n choose np into 1 plus epsilon. And that is the only thing that I have done over here. I've replaced each n choose m with n choose np into 1 plus epsilon. Okay. So now I can just take this summation outside, and what do I get? N choose np into 1 plus epsilon, because after all this is now independent of m. But how many terms are there in the summation?
around 2 epsilon times NP.
Correct. But, just 2 epsilon times NP or 2 NP times epsilon. Good. Okay. Now, of course, so I'm being a bit loose over here because I'm assuming that NP into 1 plus epsilon, NP into 1 minus epsilon are all integers. But whatever, these are just some rough calculations, right? So in principle, I should take floor and seal. Yes, question?
So, actually, I didn't understand this. Like, how you're taking in the final step is NC NP into 1 plus epsilon. In the sense, when we are considering the range, we saw that in between it is maximum.
Correct.
So, in this range of m equal to NP into 1 minus epsilon to NP into 1 plus epsilon, what
Correct.
is the reason you chose the upper bound? Uh, so, the thing is, in NCM,
Correct.
so as I start taking it like NCM is same as N minus MCM.
Correct.
So based on that, when we keep taking, it increases and then decreases. So how did you choose like how you chose M equal to N by 2 where it is maximum? How is it NP into 1 plus
So
epsilon?
that's why, right? I'm assuming that P plus epsilon is less than half. Right? So this ensures that P into 1 plus epsilon is also going to be less than half.
Okay.
So this is going to be, so NP into 1 plus epsilon is going to be strictly less than N by 2.
Okay, sir. Fine.
Right?
Thank you.
So that is exactly why I'm making this particular assumption here. Right? That P is less than half, and I'm choosing a very tiny epsilon such that P plus epsilon is also less than half, which ensures that this entire range, all of these are going to be somewhere over here. Right? So somewhere over here. So this is the range over which I'm summing. Okay, and it is possible to choose a small enough epsilon because, well, you know that P is strictly less than half. So you can choose a small epsilon, small enough epsilon such that P plus epsilon is also less than half. That's easy to do, right? Any other questions? Okay. Good. So now we are almost done. So I have n choose np times 1 plus epsilon times 2 epsilon times np. So in your assignment, you had a particular question where you obtained bounds on this particular quantity, the binomial coefficient. So what is this approximately going to be equal to? So this is going to be 2 raised to n times what?
HPN.
Exactly. So the binary entropy of P into 1 plus epsilon times whatever 2 epsilon np. So what I'm interested in is R, which is the floor of the seal of log of the size of S divided by n. So this is just 1 over n into n times h2 of P into 1 plus epsilon plus log of 2 epsilon times np. Right? So as n tends to infinity, the first term tends to h2 of P into 1 plus epsilon. What happens to the second term? It is some log, it's order log n. So log n by n tends to 0 as n tends to infinity. So this, as n tends to infinity, this entire quantity, the rate, tends to h2 p times 1 plus epsilon. Okay. So or since epsilon is very small and I can make it arbitrarily small, this is roughly equal to h to p. Right? So now we've designed a scheme for which the probability of error tends to 0 as n tends to infinity, and the rate tends to the binary entropy of p. Right? So what does this tell us? This tells us that effectively, well, most of the probability is concentrated in those sequences for which the number of ones is close to p. Right? So that is the set of interest, and the number of sequences in that set, as we know, is roughly 2 raised to n times the entropy of p. Okay, so this is really what helps. This is indeed what helps in compression. So even if you design a variable length compressor, effectively it's enough to only focus on it's enough to ensure that the sequences which are in this set have small size. For sequences outside this set, anyway, they're not going to occur with very high probability. The probability that you'll see a sequence which is not in this set is very tiny. So in some sense, if you just assign small length sequences or small length code words to sequences in this set, you're good enough. You'll achieve something close to the entropy. Okay, so this set, in fact, this can be generalized to from binary to arbitrary finite alphabets. Effectively, the idea is the same, that you look at those sequences, instead of looking at the number of ones, you look at the frequency of occurrence of each character in the sequence. If that is close to the probability of the actual probability of occurrence of that particular symbol, then so therefore S will be the set of all sequences for which you look at all possible sequences for which the frequency of occurrence of any symbol is close to the actual probability of that symbol. For all symbols. Okay, so to go from binary to arbitrary discrete alphabets, you just look at this particular set, you replace that S we had earlier with this new S, and again you can just use the weak law of large numbers to argue that the probability that xn is not in S, this tends to 0 as n tends to infinity, and it turns out that the size of S is approximately equal to 2 raised to n times the entropy of X. So this set is sometimes called a typical set. So therefore, for compression, it turns out to be sufficient to look at only typical sequences, that is the sequences in this typical set. Okay, but again, we won't discuss this in much detail in this particular course. We'll again come back to this in the source coding and the channel coding course, wherein we'll see a full proof of the general source coding theorem and the general channel coding theorem. But this is basically the idea. Yes, any questions?
Sir, how do we interpret that that statement that you wrote in S is equal to xn,
Right.
xn
So,
minus 1?
okay. So the way to interpret it is just a generalization of the binary case. So let us look at any sequence xn. So take any IID sequence xn where each xi is drawn from some set of symbols, maybe alpha, beta, gamma, delta. Okay, let's assume this is our alphabet and you're observing an IID sequence. So if n is large, then roughly how many alphas do you expect to see in the sequence?
So can you repeat?
So let us assume that the sequence consists of alphas, betas, gammas, and deltas. This is my alphabet. Okay. So whatever alpha, beta, beta, delta, delta, alpha, gamma. Okay. So all the sequences look like this. So this is my xn, right? And the assumption is that each xi is drawn IID according to some distribution px. So if I observe a long enough sequence, then roughly how many alphas do I expect to see in the sequence xn?
N times probability of alpha.
Exactly. So roughly you'll see n times px of alpha. Similarly, how many betas do you expect to see? N times px of beta, right? And that is exactly what this is saying. So you look at all those sequences for which the fraction of times, say, alpha occurs is close to the probability of alpha. The fraction of times beta occurs is close to the probability of beta. The fraction of times gamma occurs is close to the probability of gamma, and the same for delta, right? So that is what this statement is saying, that the fraction of times A occurs in the sequence is epsilon close to the probability of A. And this is true for all A's. So in other words, for alpha, beta, gamma, and delta. Right? Is that clear?
Yes, sir.
Okay. Great.
So in another inequality, um, you give something like this, whatever this mu a of xn minus px of a, that is the probability that it's greater than epsilon is tending to 0.
Correct.
So this is now here, how is this different from that? And in a sense, like intuitively, how is this different
How is what different from what?
from what you have written here, sir? S equal to this xn such that
This,
um,
yes. How is this different from?
like in another place, we had written the same thing, like the LHS of the inequality was same,
Yes.
and RHS was like, I mean, we are saying LHS is greater than epsilon, so that
Correct.
probability is
So that
tending
is
to.
just the complement, right? So I have this. So this is S, right? So this is my S. So what is S complement going to be?
Okay,
It is a
this
set
means
of all xn such that xn minus px of a is greater than or equal to epsilon times px of a. What is the rest of it? So in this case, this quantity should be less than p of a for all a. So what will the complement be? So this is greater than or equal to epsilon p of a for some a, right? So for some, that is, or for at least one a in x, right? So if this property is, so S complement is the set of all sequences for which this property is violated, and, or in other words, this property is violated at least for one a, right? If it is not violated for any a, then of course it lies in S. If this property is violated for at least one of the symbols, then it is in the complement. So this is the conditions for violation, and this violation should happen for at least one a, right? And therefore the probability of error is the probability that you observe a sequence from S complement, which is basically the probability that this happens for at least one A. Is that clear?
So,
Yes.
okay. Okay, sir.
Any other questions?
So for the S complement, when I say this statement I make, so for the probability of this to happen, it won't tend to any value or
Which one?
the S complement, sir.
The probability that xn is an S complement, so this will tend to 0, right?
Okay.
And why is that the case? So the probability that whenever this happens, is less than or equal to by the union bound the summation over all possible A of this, right? And therefore, but by the weak law of large numbers, each of these tends to 0 as n tends to infinity. So each of these terms tends to 0 as n tends to infinity by the weak law of large numbers, right? Or whatever, you can use Chebyshev's inequality. Remember that in the assignment, you derived a bound on this particular quantity. Any questions? Okay, so this sort of with this we'll kind of wrap up our discussion on source coding for now, and then we'll move to the problem of channel coding. But before that, maybe we can have a very quick quiz. I will assign that. I have assigned the assignment. It's also there in the chat box over here. You can take a couple of minutes. Again, it's very simple.
So how many more minutes? Like
You
within what time you
can
have to
take
submit?
maybe 2 more minutes.
Sir?
Yes. Oh, oops, sorry, I didn't realize that was muted. You can take 2 more minutes.
Okay.
Is everyone done?
Yes, sir.
Anyone yet to submit their solutions? Anyone yet to submit? Okay, so I'll assume that everyone has submitted, and I'm going to stop accepting responses. All right. So there was two questions. One was if you want to compress a Bernoulli 1 sequence, then how many bits do you need? What is the minimum expected compressed length? So the answer to that is 0. As we discussed in the last class, you don't really need to send anything because you know that p is equal to 1. So it is always going to be an all 1 sequence, right? And therefore you can achieve 0 probability of it. And that is because we're assuming that p and n are assumed to be known to both the encoder and the decoder. And in the other case, of course, the minimum rate of compression is equal to the entropy. And as we saw, the entropy will be the least for the Bernoulli 0.8 sequence. So h of p is, so the farther you go away from half, the lower the rate of compression will be. And so you had, I think, 0.4, 0.4, and then I think 0.5, 0.5, I think 0.55, and I think 0.8. So this is going to be give you the least rate of compression, right? So it's for the Bernoulli 0.8 source. Okay, so now we'll move to a different topic, which is channel coding. Okay, so we've talked a fair bit about data compression. Now we'll move to a seemingly completely different topic, which is how do you communicate reliably in the presence of noise, right? And it would seem that these are almost completely unrelated problems, but then it turns out that the underlying quantities are very closely interlinked to one another. So let's think about a typical digital communication system, right? So you have some kind of a source signal in a digital communication system. You have a source signal. For example, let's assume that you're talking on your cell phone to someone else, or maybe you're just communicating with the base station or whatever the tower, cell phone tower. And so your source signal, which is perhaps your voice signal, maybe you're talking on the phone. So this, of course, you can't send it directly. This first needs to be sampled and converted from analog to digital. So there is sampling, there is quantization, etc. going on. So you convert your source signal, right, which is some continuous time signal, into a sequence of numbers, right? So these are converted to a sequence. These are sampled and then they're converted from analog to digital. So you will have, let us say, M1 up to MK. So the source signal, this is a continuous time signal of duration maybe t seconds, is converted to a sequence of bits, maybe a sequence of k bits, right? Or a sequence of k symbols. Maybe each you sample the signal at certain time instance, at maybe k time instance per t seconds, right? So this corresponds to a k length sequence coming from some alphabet, right? And now these symbols, I mean, you don't directly send them directly. You convert this into a sequence. You first compress the sequence using a source coding block. So you compress this to give some other sequence. Let's call it C1 to let's say C little m. And after they are compressed, they need to be sent across the channel. Now let's sort of jump from here to the communication medium, right? So if you look at a typical wireless communication medium, there is going to be interference, there is going to be additive noise, there is going to be attenuation. So there's a whole bunch of different factors which are going to come to play. So note that this is a continuous time signal system. That is, your source signal is typically continuous time. In certain applications, it is not a continuous time signal. For example, if you want to send maybe an image or maybe you want to send a text, then this is not continuous time. But potentially it could be a continuous time system. And the communication medium, of course, is a continuous time system. But then there are some other blocks. There is a modulator and the demodulator, which basically converts whatever discrete time signal you give as input to it. So this is going to convert it into a form which can be sent across the medium, which can be sent across through the antenna. Right. So we have a modulator, we have a digital to analog converter, which converts whatever a sequence of bits or a sequence of symbols in some finite alphabet to a continuous time signal, which is sent across the wireless communication channel, or it could be a wired communication channel, it doesn't matter. Now at the receiver, you have an identical set of blocks. The continuous time signal that you receive at the antenna, at the receive antenna, this is converted from analog to digital and then demodulated to give a sequence of bits, and all of these have to be sort of converted back into the original signal. So you have a reconstruction and D to A conversion at the last step. Before that, the compressed sequence, assuming that everything went well, at this stage you should have C1 to Cm. At this stage you should have M1 to Mk, and then you get back the the decoded signal, which hopefully looks or sounds like the source signal, right? So our focus now will be this particular block. So you have compressed, you've done sampling, you've done A to D conversion and compression. So at the output of the source coding block, you have a sequence of bits, right? So you have a sequence of m bits, and somehow you need to send these m bits across a noisy communication medium such that at the end you can recover these m bits reliably, right? So for this is going to be sort of the exact, not opposite, but the dual of the source coding block. So the goal of the source coding block was to remove whatever redundancy was there in the system, right? So for example, when you had a Bernoulli P source where P is much smaller than half, very close to 0, then you know that at the end length sequence contains much fewer than n bits of information. So therefore you could compress it such that so that you removed all the unnecessary redundancy that was present in the sequence. And what the channel coding block does is sort of the dual to this. You add redundancy to the sequence, you add controlled redundancy to the sequence, and such that even though some of the bits could be corrupted when you receive, these bits can be corrected, right? So the source coding block removes redundancy, whereas the channel coding block adds redundancy, but it is not any sort of redundancy. So it is controlled redundancy. So you add redundancy in a careful manner such that even though some of the bits could be in error, some of the bits could be maybe flipped or whatever, corrupted by the channel, you can still recover back the original information from that. Right? So that's the goal of channel coding. And the way we model the whole problem is that we'll treat this entire thing, all of this modulation, D to A conversion, and the actual communication medium as a black box. Okay, and this is going to be our effective discrete channel. It's going to be a discrete time system. This entire box over here is going to be going to work like a black box, which I'll call the effective channel. So the channel will take an n length sequence as input, and it's going to output a sequence of length n. So this is the input sequence, this is the output sequence. But now what is the relationship between the input and the output? We'll assume that the output is random, conditioned on the input. So the channel introduces some randomness, introduces some corruption in a random fashion. So there is some distribution Pyn given Xn. So conditioned on Xn, the output is random and is distributed according to Pyn given Xn. So this is what we'll call the channel law. All right. So assumptions will be that time is slotted. So these are discrete time signals, and this channel law is known to us. We'll make some more assumptions as another simplifying assumption as we'll go along. But then this is going to be our basic model for the channel. So it's a random black box. It's a black box which introduces some randomness to the system. This is the transmitted signal, and this is going to be our received signal. All right. So let's stop here. Any questions? Any questions? Okay.
So this channel block that you're saying, is it like consisting of channel coding, modulator block?
No. So it only consists of the modulation and the A to D conversion. right? So if, for example, if you assume that the output of the channel coding block is a sequence of bits, then the modulator maybe first converts this to whatever modulation scheme. So for example, if you are using something like QAM or QPSK or whatever, then the modulator block does converts this to a QPSK symbols, and then converts, and from that you add a carrier signal, and then you communicate, right? So all of these things are included within this block, but the channel coding, the addition of redundancy is done prior to this. So this is going to be my channel from now on.
And so, what is the output of channel coding block? Like it receives an compressed signal and outputs as.
So I'll get to that point in the next class. So it outputs another sequence of length n. So I haven't introduced that. So for now, so this block over here, this channel block over here accepts n symbols from some alphabet as input and outputs another sequence of n symbols somehow. We'll get to that in the next class, but for now, it's all you need to keep in mind is that modulation, D to A conversion, and the actual transmission across the wireless or wired medium, all of this is sort of included within this block. We don't care what kind of a modulator you use, whether you use QAM or BPSK or QPSK or anything, and it doesn't matter what carrier signal you use, what frequency you're transmitting in, whether this is a wired medium or a wireless medium, doesn't matter. So all of this is going to be completely captured by this particular channel law over here. So for us, our channel is going to be a black box. It doesn't matter how you're implementing things within this block, but then the assumption is that for us, all that we care about is this conditional distribution of yn given xn. So this is going to be an abstraction of this entire block over here. All right. So from the next class onwards, I'll talk about this abstract channel which takes as input n symbols from some alphabet and outputs n symbols from maybe some other alphabet, and the output is a random sequence which is conditioned on the input sequence. Okay. All right. Any other questions? Okay, so if not, then we stop here.